Let's solve this tough geometry problem. Let ABCD be a cyclic quadrilateral with angle BAD is less than angle ADC. Let M be the midpoint of the arc CD not containing A. Suppose that there is a point P inside ABCD such that angle ADB is equal to angle CPD and angle ADP is equal to angle PCB. Prove that lines AD, PM, BC are concurrent. Okay. So there's a lot going on in this problem. So let's break it down. So if we draw a good diagram, we might notice that these two parallel lines hold. And so we'll prove that that's actually true. So note that there's exactly 1 point for P because this angle is fixed and this angle is monotonically changing, which means that there's only one angle for P, one point, possible point where P can be. So we'll prove that the actual point P satisfies these. In other words, we'll prove that if the intersection of the point P that satisfies this satisfies the angle conditions in the problem. So we're assuming that the parallel line conditions hold, and we're proving the conditions in the problem. Let's start by proving that this black angle equals this black angle. Okay. So note that this angle is equal to this angle by the parallel lines, and this angle equals to this angle by the parallel lines as well. And we want to prove that those two angles are the same. And so that is equivalent to proving that these two red angles are the same. Because if those two red angles are the same, then these two angles are the same. And then that's obvious. So we just want to prove that the two red angles are the same. But that's true because of the inscribed angle theorem, because this arc equals this arc. So therefore, the two red angles are equal, and so the two black angles are equal, so then the two purple angles are equal. So now we just need to verify the second, we start with the second. So now we need to verify that the first condition is true. The angle AD, that the two green angles are equal. So how do we do this? So we know that the parallel lines is true. So let's try using that to our advantage. So angle DPC is equal to this angle. And by the parallel lines PC and AM, that angle is equal to this angle. And by the cyclic quadrilateral ADMB, that angle is also equal to this angle, which is what we desired. So therefore, we know that these parallel lines hold. Okay, so now let's prove that these two triangles are similar. Angle PDC is equal to angle MAB. So that's this angle and this angle. Okay, so let's look at, so we know that by the parallel lines, which we proved earlier, that angle is equal to this angle. And note that the two black angles are equal because of the inscribed angle theorem, which we discovered earlier. So let's just say that the blue angle is equal to x, and we'll do some angle chasing. And let's just say that this black angle is equal to y. So then this angle here is equal to 180 minus x minus y. And by cyclic quadrilateral DCBA, we know that this angle is equal to x plus y. And so since the black angle is y, then this angle must equal to x, which is what we desired. So therefore, this is true. And so similarly, we can find another angle condition. And so then these two triangles are similar. So the other angle, yeah. So these two triangles are similar. So let's try using that to our advantage. So we know that triangle PDC is similar to triangle MAB. So then that implies that this is true because of the similar triangle's length thing. Okay. So now so now we're gonna try to like actually solve the problem in the next few lemmas. So let's start by proving this angle condition, this area condition. The area of triangle BMC over the area of triangle BPC is equal to the area of triangle AMD over the area of triangle APD. So let's use 1/2 AB sine C on these. So because we know a lot of angles. So the area of triangle BMC is equal to 1/2 times BM times BC times the sine of angle MBC. That's over the area of triangle BPC is equal to 1/2 times PC times BC times the sine of angle PCB. And this equals to 1/2 times, for AMD, it's 1/2 times AD times AM times sine of angle DAM over 1/2 times, for APD, it's 1/2 times AD times DP times sine of angle ADP. Okay, so we want to prove that these are equal. So right away we know that we can cancel these out and these as well. So note that the sine of angle MBC is equal to the sine of angle DAM because we know that those two angles are equal by the inscribed angle theorem. So we can cancel those out. And the sine of angle PCB is equal to the sine of angle ADP because that's an angle condition given in the problem. So then this is basically proving that PM over PC times AM over is equal to AM over DP. And we know, this should be a B. And we know that this is the exact same thing as this. So therefore, we've proven this. Okay, so we know that this is true. All right, so let's try proving that we can just replace all the B's and A's in the previous lemma with X's. So in other words, we can prove that this is still true. Okay, so the area of BMC over the area of BPC. So notice that those share the same base. So then that is just equal to this altitude over this altitude. Actually reversed. So this altitude over this altitude. And so similarly, notice that AMD over APD is equal to this altitude over this altitude. And so for the blue one, so what's also equal to the shorter altitude over the longer altitude? Well, it's XMC over XPC because those two triangles also share the same base and have the same altitudes. So then that means that we can just replace this. Similarly, we can replace this. Okay, so then that proves this lemma. So now let's actually solve the problem. So let's just define. So I forgot to mention this, but we're defining X as the intersection of AD and BC, and we're going to prove that P, M, and X are collinear. And we did not assume that P, M, and X are collinear in any of our calculations, but we did assume that it lies on AD and BC. So that's how we're defining X. So now we're going to actually prove that P, M, and X are collinear using this area formula. So, okay, so the area of XMC, so we just draw these altitudes. So that's the altitude from C to MX, and that's the altitude from C to PM. And so based on this condition, we know that these two altitudes have to be the same by base times height over 2. Because the ratio of the bases is the same. So if the altitude from C to PM equals the altitude from C to PX, then that means P, M, and X are collinear. So that solves the problem. Thank you for watching.